Hello again, welcome again to modeling methods in mechanical engineering, and today we're going to continue our discussions on differential equations. We have gone through a comprehensive summary of ODEs. This is just a refresher from when you took ODEs at the undergraduate level. And then we went from there to numerical solutions of these ODEs. So we explained how to get to the answer analytically. But we also explained that this is only possible for a very small subset of such differential equations, at least first order ones. If the equation is linear, yes, we can always find a solution, but if the equation is nonlinear, then we're out of luck. There's only a few exceptions for which we can find an analytical solution, and therefore we formulate numerical techniques to approximate the solution. As we explained, these numerical techniques are based on approximations that rely on the premise that instead of finding a continuous distribution of the solution over time, we find a discrete distribution. So basically a collection of points over a discrete collection of time values. So we call these time values time levels, and the separation between these time levels is time step. We also learned that there's not a unique way of doing this, that we can increase the order of approximation by either decreasing the size of delta t, but there's a limit to that, and so we increase the order of the approximation, which basically entails increasing the truncation level or delaying the truncation level and the Taylor series that approximates the derivative. This basically minimizes, reduces the truncation error. We also learned that we can do a combination of things, which also involve adapting the time step, so we don't always have to keep it constant, so we can change it to basically seek a tolerance or try to satisfy a tolerance. So what we're going to do today is we're going to continue along those lines. We're going to go back to an analytical formulation, but now of systems of equations, because in many instances in science and engineering, field problems are governed not by one differential equation or by one set of coupled differential equations, but instead by a system of differential equations that essentially govern different state variables or different parameters at different locations or different elements within a system. For example, in an electric circuit, you can establish a separate first order differential equation for every inductor in a circuit and for every capacitor in a circuit, and they're all tied up in the system of equations through laws such as Kirchhoff current law and Kirchhoff voltage law. The same thing you can do in hydraulics. You can have a hydraulic system where every single inertia element can be depicted in a single first order equation. Every single capacitance element or the compliance of a vessel, for example, can be also encapsulated into a single differential equation, first order differential equation. And all of these elements can actually join together in a whole system by establishing some laws that are governed by, for example, the conservation of mass and conservation of momentum and conservation of energy. And that way we arrive at a system of differential equations that govern the hydraulics behavior of the entire system. The same thing applies to mechanisms, for example, or systems of springs and dashpots. If you have a single spring and a single dashpot, you end up with a second order differential equation. But if you have a combination of in a mechanical system where you have multiple elements, multiple springs, and multiple dashpots, you can actually formulate the equations that govern the behavior of the system as a combination of first order differential equations for every dashpot and for every spring, and then combine them together by establishing connectivity, establishing what happens when two springs are in series or in parallel, and following along this line, you end up with a system of coupled differential equations, first order differential equations. So what we're going to do is try to first of all formulate the systems analytically, see if there's a hope to get to an analytical solution, and if there is hope to get to an analytical solution, an exact solution, what are the constraints and what are the limitations of a method like this? And if not, then what we'll do, and this is something that we're not going to do today, we're going to do next class, is we're going to generalize the systems and try to solve them through a generalized approximation technique, akin to the ones that we use for single system or single equations. So this is modeling methods in ME. And we'll analyze systems of first order ODEs. So often, engineering and science problems are governed by a system of coupled ODEs, and that stands for ordinary differential equations, where the unknowns, y1 of time, y2 of time, y3 of time, and as many as you may have, represent the state variables of specific instances in the field, i.e., as I mentioned, there can be currents and voltages in an electric circuit. It could be flows and pressures in a hydraulic circuit or system, location of different points in a kinematic system, etc. There are many things that can be formulated this way, and where the representation of the system is in terms of these so-called state variables, where the different y's, again, are not y1, y2, y3 are not y's at different time locations. These are very essentially the different state variables. One can be a pressure, the other one can be a current, a flow, volumetric flow rate, the other one can be a pressure at another location in the circuit, and so on and so forth, over time. So we're still talking about initial value problems. As you can see, we're formulating this in terms of variables that depend on time. So we are going to write the system of equations as follows. So we have the equation for variable 1, which is y1 as a function of time, is equal to some function 1 that is a function of t, and function of 1 at y1, y2, all the way to as many state variables you have in the system. And as such, you would have another equation for y2 that is a function 2 of time, y1, y2, all the way to yn, and ending with an nth equation, which is again a first order ordinary differential equation that governs yn, which is a function n of time and all state variables. So as you can see, there's as many unknowns as you have equations. There's n equations for the n unknowns y1 through yn. Again, y1 through yn are n different functions of time. Okay, so we can encapsulate all of these into a single equation. We use that squiggle there in the bottom to denote that y is really a vector of functions, and f squiggle is a vector of functions. All right, so in addition to having n differential equations for the n functions that we're seeking, which now we call state variables instead of functions, we also would need a complete set of initial conditions. That is, we need to know what each one of these functions y is at time equals 0. That is, we need y1 at time equals 0, y2 at time equals 0, all the way to yn at time equals 0. And we can denote that as y1 0, y2 0 or not, all the way to yn not. So these are all the necessary initial conditions that are required for a complete set. Now, if the system of ODEs is linear, the solution exists and it is unique. That is, there is a vector of solutions, yt, that contains a single and unique y1, a single and unique y2, and a single and unique all the way to yn. So that vector exists, and it contains n unique functions, different from each other, plausibly, and in general sense. Now, a linear system of ODEs can be expressed as so instead of writing it in terms of these functions f, which basically generalize the equations to be either linear or nonlinear, let's now be specific and say that these equations are linear. So it would be, start here, dy1 dt is equal to sum a11 of t times y1 plus a12 of t times y2 plus a1n of t times yn of t plus g1 of t. That's g1. Then the second equation we can write as, again, remember these are first order equations. So it's a linear, because the equations are linear, they are a linear combination of different coefficients. And notice that I'm generalizing this to denote that the coefficients could be a function of time. So these are variable coefficients. And all these coefficients are different, potentially different. All the way to the nth equation. We have these down here. dy and dt, and yn is also a function of time. an1 of t, y1 of t, is an2 of t, y2 of t, plus ann of t, yn of t, plus gn of t. So notice that we have again a complete system of n equations for the n different unknowns that are separated by distinct coefficients, and we have independent terms here, the non-homogeneous independent terms at the end. All right. So the reason why this system is called a coupled system is because you cannot solve for any of these equations individually. Because in order to solve for y1, although this is a linear first order equations which we know how to solve, we would need to know y2, y3, all the way to yn. We cannot solve for these equation without solving the second one. And we cannot solve for the second one without knowing the first one, and so on and so forth, for all equations in the system. So they're coupled, meaning they cannot be solved independently without one without the other. So these set of equations right here, as you can see, is just that we can express this in matrix and vector matrix form very easily by collapsing this whole thing like this, or in compact form, we can have y of t. So I've replaced the squiggle with a set of squiggly brackets, and on the left hand side we have y dot, which denotes the derivative with respect to time. It's equal to some matrix of coefficient that we call A of t. That includes all these A11, A12, and all these distinct coefficients, which could potentially be functions of time. That makes them variable coefficient. Times y of t. So every one of these coefficients multiply the y of t, plus a vector of independent terms, g of t. This is the state representation of the system of equations. This is a linear system of ODEs, in particular first order ODEs. So these vector y dot of t contains the elements dy1 dt, dy2 dt, all the way to dyn dt. The element y of t contains y1 of t, y2 of t, all the way to yn of t, while the vector g of t is the vector of independent terms, contains g1 of t, g2 of t, all the way to gn of t. So these are column vectors, as you can see. And the matrix A of t is the matrix of coefficients, which we're denoting to be variable coefficients. It could be functions of time. These are A11 of t, A12 of t, all the way to A1n of t, A21 of t, A22 of t, all the way to A2n of t, an1 of t, an2 of t, all the way to ann of t. And you can see the diagonal here. By the way, not all of the elements in this matrix need to be different than 0. If this matrix is diagonal, meaning that all the off-diagonal terms are 0, then the system is not coupled. Then you can solve each equation individually, because basically dy1 will only be a function of y1, dy2 with respect to time will only be a function of y2. That's only if this matrix is diagonal. But in the general sense, this matrix reflects a fully populated matrix that reflects the fact that this is a coupled set of equations. Now, if g of t, which is the vector of independent terms or the non-homogeneous elements, is equal to 0, so if all these functions are equal to 0, not just one of them, if all the functions are equal to 0, then the system of ODE is homogeneous, or homogeneous, whichever way you want to pronounce that. If the matrix A of t is just simply a matrix of constant values, then the system of ODEs is constant coefficient. And if that's the case, then we can express this y dot is equal to a times y. And this is a linear, homogeneous, constant coefficient coefficient system of first order ODEs. Now the reason that I am bringing it down to the simplest possible case, I'm simplifying this to just a basic linear homogeneous system of equations, is because this one is the one for which an analytical solution method exists. If the system is other than this, then we have to rely either on very exceptional cases to get an analytical solution or in approximate techniques to get us to an approximation of the solution, as we'll see next class. So for this class, we're going to concentrate on this very simple case where the system is homogeneous, is constant coefficient of first order, linear first order differential equations. Again, if you look at this system, because it's fully homogeneous, an obvious solution to the system would be that y is equal to 0. Because if all the y's are equal to 0, then all its derivatives are equal to 0, and then 0 is equal to 0. So that's fine, that applies. As we would find for a single differential equation, if you have a single differential equation and the differential equation is homogeneous, there's no independent term, a possible solution is a trivial solution. Essentially, the solution could be equal to 0. That's trivial. However, for the solution to be non-trivial, we will have to have what's called a non-homogeneous initial condition. At least one of the initial conditions for y would have to be non-homogeneous to get the system out of triviality. So let's explain that with, and we already explained that here, but let's explain that with a single equation. So if a given single ODE, so we have dy dt is equal to a pi. So this is kind of the single ODE that emulates the system of ODEs, sort of the same thing. So it's again linear, homogeneous, etc., etc. with a homogeneous initial condition. So that means if I give you this equation and I tell you that the initial condition is also 0, then what is the solution? Y of t. By the way, this is y of t, okay? It's implied. What is the solution to the system? Obviously, the solution would be 0. So we can try to get the solution. Well, obviously this equation is separable, right? Or you can just simply use a general solution for a linear first order ODE, which in terms of an integrating factor. But this one's very simple because I can send the dt to the right hand side and then the y down here. So I get the integral dy over y is equal to a times the integral of dt. So I get the log of y is equal to a t. That means that y is equal to e a t. So the solution, the general solution, would be y of t be equals to a constant times e to the at. Okay, and try that. You take that general solution. It's general because we have a constant of integration right there. You take that, take the derivative of that, and that would be ca times e to the at. That goes on the left hand side, and then multiply that times a. That will be ac e to the at. The left is equal to the right, so that yes, that actually satisfies the governing equation. Now let's find the constant of integration c using the initial condition, and that would mean apply initial condition means that y of 0 is equal to 0, so would be c times e to the a times 0. So at time equals 0, the solution y is equal to 0. That is 1, and then that just simply means that c is equal to 0. So if c is equal to 0, then the particular solution if this is general solution and c would give you the particular solution, then y of t is equal to 0. So this is a trivial solution. Sorry. This right here is a trivial solution. All right, and we don't want a trivial solution, but that's what we get in this combination. There's no way around this. Okay, this satisfies the governing equation, and this satisfies the initial condition. At time equals 0, it is equal to 0. Yes. So therefore, if the homogeneous or homogeneous system of ODEs is given as y of t dot equals a y of t, at least one initial condition for any of the functions y1, y2, y3, or yn, at least one of them must be non-zero for the solution y of t to be non-trivial. Otherwise, we're back down to the solution being equal to 0, and, well, that's trivial. So for the solution to be non-zero, at least one of the initial conditions needs to be non-zero. All right. So now let's formulate an analytical approach to this based on the fact that if we have a single equation that looks like this, the solution looks to be exponential. So we're going to use this as an analogy to show that, well, if this happens to be a system of multiple equations and multiple unknowns, we expect the solution to sort of behave the same way. All right, so an analytical solution of this system of ODEs may be attempted by recognizing that a single ODE, again, if we have a single ODE like this one, dy dt is equal to some coefficient a times y of t, has a general solution y of t equals to a constant of integration e to the at. Right? So we know how to get that by separation, and we know where the constant of integration comes from. Therefore, it may be inferred that the solution of the system is, so the solution of this system up here would be y of t, so an arrangement or vector of y's, is equal to some constant x e to the lambda t. So we're going to write that and square it to denote that this is our premise. That's where we start. So what we're going to do is first plug these so-called trial solution back into the system of ODEs. Right? So if we are inferring that these satisfies the system right here, let's plug it back in and see what we find. We should find an identity. So if the system looks like y dot of t should be equal to a y of t, that is the system that is given to us, and this is the solution that we're guessing as a trial solution, then if we are saying that y of t is equal to some vector of constants of integration x times e to the lambda t, then y dot of t, so if we differentiate each one of these solutions, then we'll get lambda times the constants of integration x times e to the lambda t. By the way, I use x not to denote that that's a space variable. X is just a set of a vector that contains constants of integration. All right. So I'm going to plug these on the left and this on the right, and what I get is lambda. Therefore, lambda x e to the lambda t is equal to the matrix A times x e to the lambda t. Okay, I can see very clearly that this one and this one, the exponential functions cancel out on both sides. And what I get is, I'm going to just flip this over and say that A times x is equal to lambda times x. So this is how I get those lambdas and those x's. So solve for lambda and the corresponding x's. So see what I'm saying here, or what I'm trying to do is, we formulated that the solution of the system could actually be like this, because we know that a single equation will have an exponential type of solution. We just need to find the powers of that exponentials, and then the set of constants of integration or whatever it is that actually multiplies that. And in order to do so, when we plug that back into the set of equations, which we are inferring this satisfies, we end up with a system which seems to be sort of like an identity. If you look at this, we're saying A times x is equal to lambda times x. By looking at this, what can we say? Well, we can say that if this were numbers instead of matrices and vectors, Ax is equal to lambda x. All we're saying is that A is equal to lambda. But that's not possible in a matrix system because this is dimensionally incompatible, right? A is a matrix that has n by n elements, and lambda is just a number. So we can rearrange this and turn it into a so-called eigenvalue problem by basically stating, right? So see how we solve for these seemingly unsolvable problem, or trivial problem nonetheless, because if x is equal to x, obviously, then A has to be equal to lambda, but there's a dimensionality issue there. What we say here is that this system, this expression, is known as an eigenvalue problem, where lambda is an eigenvalue and x is the corresponding eigenvector. So what this basically means, eigenvalue is an auto value. Eigen is an German expression, I believe, for automatic. It just basically says that there's very special values in this set of equations of gamma that make these expression non-trivial. Because the other way of looking at this expression, if you omit the dimensionality issue, so A is a matrix and lambda is just a number, it's a scalar, is by looking at the x's. The solution for this system, for this expression, is x is equal to 0, right? Because if you say x is equal to 0, then the left is equal to the right. However, it turns out that there's very special, or eigen, types of values of lambda that would make the solution non-trivial. So there is a very special combination of lambda and x that would make the solution not have a 0 here on x, okay? Where x is basically the what's known as the eigenvector, which simply expresses a direction. There's a specific direction that you can rotate the system that by multiplying by a term, a very special term, lambda, would make these non-trivial, will make this valid, this expression valid. So there will be be as many eigenvalues, lambdas, and corresponding eigenvectors x's as the size, in this case n, of the system. So the size of the system is determined by the size of the matrix A, number of columns and number of rows. By the way, this is a square matrix, so I have the same number of rows and columns n, right? So there is, for a system of n equations and n unknowns, there's as many as n eigenvalues and n corresponding eigenvectors that make the solution possible. Okay. By the way, the eigenvalues, are not necessarily always real values or real numbers. You may end up with complex eigenvalues, and that has a meaning too. However, if A is a positive definite matrix, then all eigenvalues are real and positive. So what is a positive definite matrix? Well, I guess that's a kind of a circular definition, because a positive definite matrix is a square matrix for which all eigenvalues are positive and real. So there you go. So we're back to this. We have A x is equal to lambda x. And we need to solve for lambdas and x and the corresponding x's. And we know now that there's going to be as many as n lambdas and n corresponding values of the vector x that will make this possible. And if we get that solution, then we'll be essentially solving the given system of equations. Remember, we were given the system of equations, right, to which we infer the solution was like this. So if we find the lambdas and the x's, we'll basically be finding the solution. In order to find the lambdas and the x's, we need to solve this adjoint problem. This is the problem that arrived from inserting the trial solution into the system of equations. So now let's insert the identity matrix. So this right here, A times x, should be equal to lambda I times x, right? So such that I is the identity matrix. And remember, the identity matrix is a matrix that has ones at the diagonal, 0 everywhere. Is essentially the equivalent of 1, of unity, in matrix. So a square matrix with ones at the diagonals and zeros elsewhere is a matrix that you multiply by anything and you get that anything. So it's equivalent to the number 1, essentially, in algebra. So if this is the case, then I have something that is dimensionally compatible. I can send this over to the left-hand side and say that A minus lambda I times the vector x should be equal to 0. And by the way, this is a matrix times a vector, which should yield a vector. So this should be a vector of zeros, technically, right? You have 0, 0, n zeros. So this is just another, I've just sent this over to the left-hand side and I end up with these. All right, so in order for these times this to be equal to 0, there's two options. For the expression above to be true, either x is equal to 0 or either x is equal to 0. So we have a product here of two things. This times this equals 0. So in order for that to be equal to 0, either this is equal to 0 or this is equal to 0. Or the determinant of A minus lambda I is equal to 0. So we cannot say that this entire thing is equal to 0 because this is a matrix, but we can say that the determinant of that is 0. And if the determinant of that is 0, then when multiplying times x, we should get 0. Right. So the option of letting x equal 0 is not a valid one, because if we let x equal 0, then we go back to this solution being trivial, being 0. So that's not a permissible one. We don't want the solution of the system to be trivial. We're looking for a non-trivial solution. So since the option x equal 0, which by the way is also a vector of zeros, leads to a trivial solution. So remember that y of t was set to be x times e lambda t, and therefore if you let the x's be equal to 0, then the all y's of t's will be equal to 0, and we don't want that. Then the only admissible choice for a non-trivial solution is that the determinant of A minus lambda I should be 0. So we know what the matrix A is, the lambda we are trying to find. I is a identity matrix, we know what that is. So if we solve this equation, then we should get a non-trivial solution. So we can solve this equation for the n values of lambda. So this solution of the equation that says that the determinant of A minus lambda I equals 0. So if we solve that equation, leads to the eigenvalues lambda as many as the size n of the matrix A. So this will lead to a system of linear equations for lambda. Okay, so just coupled equations, not differential equations, just coupled equations. So once the eigenvalues lambda are determined, the eigenvectors x may be found using the original expression that says that A minus lambda I times x should be 0. So we plug in each of the value of lambda, and then we should get each of the values of the eigenvector. So plug in each separate eigenvalue, sigma n, to derive each corresponding eigenvector x n. So what happens then is leading to the solution of the system of ODEs S. So once we determine each eigenvalue and each corresponding eigenvector, we can then say that the solution y1, we have a possible solution y1, which is equal to the eigenvector 1 times e to the lambda 1t. We have a set of possible solutions y2, which is the second eigenvector times e to the lambda 2t, and all the way to an nth possible solution, which is the nth eigenvector times e to the nth eigenvalue times t. So using superposition, we can express the final general solution y of t in terms of a linear combination of the different possible solutions above. That is, we can say y of t is some c1 times the first eigenvector times e to the lambda 1t plus c2 times the second eigenvector times e to the second eigenvalue t, plus all the way is as many elements we have in the system, Cn, times the nth eigenvector times e to the nth eigenvalue t. And that is the general solution. This is the general solution to the ODE system y dot of t is equal to a y of t. Remember, this has to be linear, as it shows. It has to be constant coefficient, and it has to be homogeneous for the solution to be this way. Okay, and such that there's n equations in the system, and therefore that leads to n eigenvalues and n eigenvectors. So that's it. This is the theoretical foundation as to system of differential equations, for which you need some notion of linear algebra, matrices and vectors. And next class we'll get together and solve an example problem, and then show how we can actually approximate the solution using an extension of the different approximation techniques that we've actually implemented already, namely the Euler, the modified Euler, the Hoynes, the Runge-Kutta, or any predictor corrector numerical integration scheme. So we'll compare what we get with solutions with numerical approximations and analytical solutions. Again, this analytical solution method is confined to systems like this, very simple, linear, homogeneous, constant coefficient systems. If the system deviates at the very minimum, or even slightly from this, then this technique doesn't work. That is, if at least one of these coefficients in the set of equations is variable, or if you have at least one non-homogeneous term in the set of equations, then that's it. The system stops working. So that's all I wanted to convey today. This will be posted as always, and thank you for your attention, and I'll see you next time.